Okay, I'm back with you. I had a brief interruption there. Okay, so to get exactly what we want, we need a CV of 24. But if you go back up, we don't really have a 24 on the list, and so we have to go down in size. If we picked a larger CV, we would get a smaller pressure drop than our 10 feet. And so looks like 21 here. Let's see what they select on this. Yeah, so he's going to pick the closest valve with a slightly smaller than 24 CV is the 1.5-inch valve. And so you can look, there it is. That's the largest CV under the 1.5, and that's the one that's closest to 24 on the low side. So that's what we're going to select. So then now we have to take that CV back to the valve equation and then calculate what the actual pressure drop is going to be. So to do that, I take my 50 GPM and divide by 21. I get that's 2.38. And now I'm going to have to square this, squared, and that's 5.669. And then that's PSI. That would be the PSI drop. There's no specific gravity adjustment. And so times 2.3 is equal to 13.04. So it comes out right on 13 feet. And so with that CV valve, with it wide open in a wide open position, we would have 13 feet. And so that makes the circuit one loss the 18 feet plus 13 feet. So it's 31 feet. So now our goal is going to be able to match, is to try to match that 31 feet on circuit 2. Okay. So if we did that, we already have 12 feet in everything else but the control valve. So when I take that 31 minus 12, I want 19 foot drop across that control valve in the wide open position. So I want to select a CV to do that. Okay, well, so let's do that. So let's see. So 19 feet, I'm back to we're going to use that silly little equation to death here. So 19 feet divided by 2.3 is 8.26. And I want to take the square root of that. And so I get 2.874. And I'm going to store that away in my calculator. And now this flow rate is 30. So 30 divided by that 2.874 is 10.43. And he's rounded it to 10.5. And now he just wants to get now if you pick one smaller than that, you're going to increase the total pressure drop. Then this circuit would have a higher pressure drop than the first one. And so then you would wind up operating at a little bit higher pressure. So in this case, we're going to go down. I'm sorry, we're going to go up. I think I said that backwards. So if we selected a smaller CV, then we would up the pressure drop in the system. So we want to select 11, which is slightly larger because we don't have 10.5 as an option. Again, we're looking for something slightly greater than 10.5. And while under the 1.25, the middle orifice has an 11, which is perfect or pretty close to perfect. And so we're going to have an 11 CV. So now I take my 30 GPM divided by 11 equals that. That's 2.727. I'm going to square it, and that's 7.438, and that's PSI. And then I'm going to multiply times 2.3, and I'm going to get 17.1, which he's going to throw away the 1. And so the 17 plus the 12 gives 29. And so the first circuit is right at this point 31. The second circuit is 29. So that means I have to use the balancing valve in circuit 2 to crank in 2 more foot of drop in order to balance them. So we can see that we're well within 2 feet, being well within the 25% lack of 25% variation between the circuits. They're almost on top of each other. So we have done that well. So we can easily crank in that extra 2 feet on the balancing valve on circuit 2 and perfectly balance these out at 31 feet each. Okay, very good. So let's move on to example number 2. So this time we have 3 identical coils and the runouts, control valves, and all of that, balancing valves. Now, in this diagram, he's showing balancing valves, just didn't show them on the last one. And then so we have one system pump that pumps out of the discharge of the pump to point A, where we start pulling off. That's where circuit 1 pulls off. Then we go down a ways and we pull off to 2, and then we get to C, which is kind of where the branch circuit to zone number 3 pulls off. And then we come out of 3 down to D, and we're saying that the return header starts at D and then runs from D back to B, where the flows come back together. And then we have common piping from the B through the pump back to A. So all of the circuits see that same drop from B through the pump to A. Okay, so this system, it's a 2-pipe direct return. So direct return, you should know by now that if you look at zone 1, it has short supply piping and short return piping. If you look at zone number 3, it's got long supply piping and long return piping. So that's obviously direct return. And 2-pipe just means that that same coil would be used for both heating and cooling. And so in the summertime, we would run chill water through that system. And then when it gets to the heating season, we would actually have a changeover and we would put hot water through that same system. So we don't have 2 pipes indicates 1 coil. Some systems are what they call 4-pipe systems, which have 2 coils. And so there would be a dedicated hot water and chilled water coil. In this case, the same coil serves for both. So that's what that nomenclature means. Okay, so control valves again are sized for 10-foot pressure drop at 40 GPM, and all the zones are the same. And that we say that requires a CV of 19. Again, we can check that. So we want 10 feet divided by 2.3 equals 4.35 square root, 2.085, store 1. And then I take the 40 GPM divided by 2.085 divided by recall 1. And that comes out 19, really 0.18, but 19. Okay. So again, we want to be a little bit either on 19 or a little bit smaller for this first zone. So that would put us at 18 when we go back and look through the chart. 18 is the best we can do. That's a 1 1/4 inch with a large orifice. Okay, and so then when I go back to my valve equation again, that tells me that I'm going to have an 11-foot pressure drop across the valve. And so let's see, we can verify that. So again, if I take the 40 divided GPM divided by 18 equals this squared, that's 4.938 PSI times 2.3, and that's 11.36 actually, but again, he's rounding to this. So they take the 11, we have 14 for the rest of the circuit, and so that makes us 25 feet. And so now we're going to try to balance 2 and 3 to the 25 feet. Okay, now some other stuff here on getting this stuff, being able to balance this entire system. To aid in establishing design system balance, the pressure drop of AC plus BD. Now, AC plus BD is the distribution piping that affects all of these circuits. He's left off the piping from B through the pump to A because that's common to everybody. So as far as balancing out the system, that doesn't matter. But the drop from AC to BD certainly does. And the rule of thumb is that should not exceed 50% of the total branch pressure drop. Well, so we've just sized the branch, and so that's looking like it's going to be 25 feet. So the for that first zone that we just did, which means that if I take 50% of that, I get 12 and a half. So that means that the total main pressure drop connecting the three circuits should not exceed 12 and a half feet. Okay, so that's AC plus BD. Okay, assuming that these lines, AC plus BD, have a total equivalent length of 400 feet, then that says that if I take 12 and a half feet, 12.5 divided by 400, that comes out about 3 feet per 100. Okay, so that's going to be our sizing criteria to keep that drop within the 12 and a half feet total loss. Now, we also would want to make sure that the velocity is 2 feet per second or higher. He said if we follow this procedure correctly, then the variation in flow rate between the units with all the valves wide open will not exceed 10%. Let's say, okay, and so this is the sizing diagram, and this is in your homework that I have sent. So we're saying, let's see, what's our flow rate on this thing? Well, so, okay, so you have different flow rates. So from the pump to A, we have the flow rate of all, well, it's 40 each. So, but from A to this first takeoff, we have what, 80 GPM, and from the takeoff of unit 2 down to C, we only have 40 GPM, and then we have 40 from D back to the first return point on or the return point on circuit number 2, and then we have 80, and then it goes to 120. So, you know, we have, it depends which section that you're sizing. Say if we're sizing this one from A to this first takeoff, we've got 80 GPM. And so if you come over here at 80 GPM and go up, so at 80 GPM, we could not do 2.5 inch pipe. We're going to have to do 3-inch pipe. So if you come straight up from the 80 to the 3-inch pipeline and come over, it's pretty close to 1.5. It looks like it's a little more than 1.5 feet per 100 foot of pipe. So that would need to be 3-inch pipe. When we go down to 40, then we can do 2.5. Can we do 2? 2 is pretty close. If you wanted to really be careful, you could do 2.5. And again, and here's the 3. You can find the 3 foot per second or the 2 foot per second line. And so we're okay on that. So a little bit of a primer on how you use that pipe sizing. Okay. So, oh, and that's, that ends his example 2 here. He just, you go back and do the same 2 things on the other 2 zones in order to let them come out 25 or less, and then you would use a balancing valve to boost them if you needed to get them up to 25. Okay. All right. So here's example 3. This is the last of the 2-way valve examples. So here we've got 3 circuits. It's similar, but now the zone 1, zone 2, zone 3 are different. Zone 1's 40 GPM at 8 feet, zone 2 60 at 14 feet, and zone 3 is 30 GPM at 10 feet. Okay, so we're going to start with the one that has the highest pressure drop, which would be number 2. Again, we're going to select the closest available valve for 10 foot or greater pressure drop. And so we go back through the Q is equal to CV times the square root of delta P over SG. And we go through all of that, and we wind up with, and I'm going to short circuit some of that because you should be up on that by now. So we're going to wind up with a 2-inch valve with a CV of 26. And we can check that that gives a 12-foot drop. So if we take my 60 GPM divided by 26 equals this, square it, times 2.3, that comes up with 12. And sure enough, that's a 12-foot pressure drop. The rest of the circuit has 14, so that puts us at 26 for circuit number 2. Okay, looking at circuit number 1, we need 18 feet because what? I am at, I'm at 26 and I have 8. So that means that I need 18 because 8 and 8 is 26. Okay, so the closest valve to that is going to be a CV of 15, which gives, now when we went through that, we selected this CV a little bit higher because we don't want this pressure drop to be greater than that number 2. Number 2 is the lowest we can get away with. Okay, and so we select for a CV of 15. I go back through the equation and that tells me that pressure drop is 17. So 17 and 8 is 25. So that balancing valve in circuit number 1 will have to have 1 foot cranked into it to balance out and equal that of zone number 2. And zone number 3, we go through a similar situation. We need 16 because we were 10, we're shooting for 26. This requires 11.4. Well, so we don't, in this case, he has selected an 11, which is gonna increase. So this is what happens if you go down on this selection, but it's pretty darn close. So anyway, the guy doing this went ahead and went down a little bit. We have an 11.4 CV, which gives, when you go back to the equation, that gives a 17-foot pressure drop. 17 and 10 is 27. So now circuit 3 is the highest. And so circuit number 2 would have to have 1 foot put in it. And circuit number 1 would have to have another foot for a total of 2 to balance this thing out. And so that's what we're showing there, total pressure drops in the circuits. Before we use the balancing valve would be this. Again, that's nowhere close to a 25% variation, so we're no problem there. And again, if circuits number 1 and 2 have their balance valves set to bring the total pressure drop to number 3, and the main AC plus BD is no more than 50% of 27, then we'll be fine for flow variation. Also note that when selecting a pump for this system, well, 130, if we look at our flow requirements, we've got 130 G40 and 60 is 100 plus 30 is 130. So that's the 130. And notice now we don't add these up. We simply select the largest one. Okay, so a lot of times when people do this and they see these multiple zones, they think, well, I've got to add this pressure drop, this pressure drop, this pressure drop. No, because the pump establishes whatever head is required to get it through the largest. And then the others, if you don't balance them out, will just have more flow than they're supposed to have. And so that's why the balancing valves are there. But note, and you got a homework that's coming out with this video, you don't add these together, you just select the largest. Okay. The other thing that we could do, let's go ahead and select a pump. So that's 130 GPM at 27 feet of head. Let's see, I think I have, let's see, can't see for that. I gotta have to pull this down here. Let me see, I may have gotten on, I think I got on the other computer. Let me see here. I'll get on this one. We'll just go Bell and Gossett. Pump selector. That's this ESP thing. Bell and Gossett. There we go. ESP system-wise, that's what I'm looking for. There we go. That's just so easy. Okay, so pumps. I'm not sure, this is pretty small. I'm going to select an inline. These are for larger flow rates on this homework, you'll probably be over here in like the E1510. It would be a good place to start, but I'm thinking I'm going to select a couple of these. And constant speed is fine. GPM just 130 at, what was it? It was 27 feet ahead, wasn't it? Just get results. See if I don't come up with something here. Yeah, I got quite a few. So you can look at the, it's got some more stuff out here. Yeah, whatever, I can just pick one of these. Efficiency, this one looks pretty good actually. Quote series. You can download all this stuff. But anyway, that shows you a pump curve and you can download all the information. It's just a couple of clicks away. But so see, there's 125, there's about 130 GPM, and there's my 27 feet ahead. So it's not real hard. The hardest part is to figure out, well, the flow rate comes from load calculations, but knowing the head, that can take some work, as you are about to find out. Okay. All right, so let's continue on here. Example number 4, typical 3-way valve controlled 2-zone air handling system is illustrated below. Control valves should generally be rated at a pressure drop 3 times that of the coil, or greater, up to a maximum of 20 feet. So let's see, looking at zone number 1, we can see that's the one on the left, and zone number right. Zone number 1 is 60 GPM at 6 feet, and zone number 2 is 40 GPM at 5 feet. So we'll take the one with the largest drop first. So if we did a 3-to-1, so 3 times 6 is 18. So we're shooting for an 18-foot drop across the control valve at 60 GPM. So again, you can calculate the required CV from the valve equation. I think you're probably good on that right now. And so it comes out 21.4. We don't have 21.4 in our sizing chart, but we have 21. And so when we use 21, then that pressure drop instead of 18 is 19, which is fine. It's less than 20, and it's greater than 3 times, so that's good. So that's what we're going to have for the circuit on the left. Okay, so now he's going to calculate the total pressure drop for zone 1 can now be determined. And now that 6 feet, that was just a coil drop. And so that's a little different than the 2-way valve examples. But at any rate, so that puts the control valve at 19. We've got a balance valve, which is when it's wide open is 2, and he's got additional piping drop of 2 foot in there, so he gets 29 feet at the 60 GPM. So zone 2 must now be designed to match this 29-foot drop at 40 feet. Selection of the 3-to-1 ratio on the control valve. If we go back, we can see that the coil itself is 5 feet. So 3 times 5 is 15. That's what we're shooting for. However, a higher pressure drop from the valve will assist in balancing the circuit. So he's gonna, based on, I guess, some experience, he's gonna try to get a little bit higher drop across the control valve, because it's gonna help make the numbers come out. It's gonna help balance it a little bit better, a little less with the control valve. So zone 2, circuit pressure loss without the control valve. So he's got the 5, say, and the balance valve open is 2 and the piping is 2, so that's 9. And so that's a pretty far cry from the 29 that we're shooting for, you know, so he's 20 off. So a valve selected for 20 foot would balance the circuit just with the addition of the control valve. Okay, so he's going to shoot for, if you shoot for the 20 foot, let's run that back through the equation. So 20 foot divided by 2.3 is, it's about 8.7 PSI. If I take the square root of that, I get 0.29488 store 1, and that's at 40 GPM divided by that is about 13.6. So we're shooting for, so he's shooting for about a 14. He's going to put a 15 in there, which is going to give me a 17. It's a little bit larger. So instead of the 20, I get a 17-foot drop with a CV of 15 at the 40 GPM. And so that's going to put me 3 short. So I'm going to have to crank in 3 with the balancing valve in order to get this zone up to the 29 that I'm shooting for. Okay. So the bypass balance valves. So that's these little balance valves we're showing here in the bypass. They are to simulate the coil, and so they have to be set appropriately and sized appropriately. So the bypass balance valve on zone number 1 should provide 6 foot of pressure drop because that's what the coil does, and number 2 should provide 5 foot. So the CV needed by zone 1 bypass valve is 37, and it's 27 for zone 2. You should verify those numbers, but it's just using that valve equation again. Okay, and so that's the end of number 4. And the last example, here's number 5. This system has 3 air handling unit coils controlled by 3-way. These are three-way mixing valves. Control valve for zone 2, size first because it has the largest drop. We're seeing 200 GPM at 6 foot. The other 2, number 1 is 100 at 3 foot, and number 3 is 180 at 5 foot. A 3-to-1 ratio, again, 3 times 6 is 18, so that's our target. At 200 GPM requires a 72, and the closest selection to that is 68, and so that instead of the 18, and see, we want to go down because we want the pressure drop to go up a little bit more. We don't want it to be lower. And so at 68, that's going to give a pressure loss of 19 feet at 20 GPM. So again, when we look at the total for zone 2, we got the coil at 6, control valve at 19, balance valve at 2 wide open, and piping at 4. So that total zone drop is 31 feet. So assuming that zones number 1 and number 3 each have 4 foot of piping and 2 foot balance valve wide open pressure drops, they're balanced as closely as possible to zone 2, which gives the following. And so we're going to try to do this. So zone 1, it's a 3 foot on the coil, so it's 18 on the control valve, so it'd be 27. And we're on, let's see, that's a 36 on the CV. And zone number 3 with a 68 on the CV gives a 16 foot on the control valve, which is more than 3 times the coil. So that's good. So we got 27 on that one, and we got 31 on this one. So guess what? We're going to have to add 4 to each one of those. So to obtain maximum design balance, the total valve plus coil pressure drop should be equal for all zones. Minor differences can be made up by mechanical balancing. Bypass valve should be set to create the same pressure drops as their respective coils at the design flows. Total pressure drop of the distribution piping, AB plus CD in this example should not exceed 50% of the individual zone pressure drops. If we assume AC plus BD is, or AD plus CD, now that should be what? That should be AB plus CD. That's a typo. Anyway, it's 300 feet. So then the allowable drop is 5 foot per 100. You just take 50% of the zone drop and divide it by the equivalent length. And since normal maximum allowable design drop for noise criteria is 4 foot per 100, even better overall system balance will result. So we're good. Okay, I know that's quite a bit, but study those things. I didn't want to drag this thing out too long for you. So I'm going to stop this now and post it. If you have questions, certainly email me and I'll do my best. I'm also going to send the homework with it, which we'll have at least 10 days to 2 weeks to complete. The homework is fairly significant. So I hope you guys are doing well, staying safe, and I'm going to go ahead and end this now. So bye-bye for now.